For this video, we're going to look at the end behavior of exponential functions. And before we dive into that complex topic, we're first going to just talk about what end behavior means for any function. Then we're going to look at the end behavior specifically for exponential functions. Alright, so suppose we have a function f. The end behavior of f is the trend of the outputs that you get when x gets really big or really negative. So if we're thinking about on our graph, we're thinking about x values that go way to the right, that's when x gets really big, and or way to the left, that's when x gets really negative. So as an example, we have f of x equals 2x plus 3. This is a nice linear function that we're familiar with. So let's see what happens when we put in some big values of x to see how end behavior works on this function that is very familiar to us. Well, if we put in, say, x equals 1,000, we get 2,000 plus 2 times 1,000 plus 3 for our output. That's 2,003. If we put in 1,000,000, we get 2,000,003. And we can see that in general, as x gets huge, 2x is going to be even huger. It's even going to be bigger. And then 2x plus 3, even a little bit bigger than that again. And so in general, as x gets big, f of x is going to get very big as well. If we want to express that symbolically, we say that as x goes to infinity, f of x goes to infinity as well. All right, so let's see what happens when we put in some very negative values of x. So go way to the left on the x-axis. So if x equals negative 1,000, we do the same computations. We end up with negative 1997. If we put in negative 1,000,000, we get, well, a very negative number. Looks like we're finding ourselves a trend. As x gets very negative, 2x is even more negative, and 2x plus 3 is a little less negative than that, but only a little, which tells us that as x gets really negative, f of x is going to get really negative as well. Formally, that's saying that as x goes to negative infinity, f of x also goes to negative infinity. And actually, we can infer this from the graph. So if we look at the graph, we can see that graph going, and its slope of the slope is 2, just as we expect. And if we think about what happens as x goes to infinity, that means we're moving to the right. So our x values are moving to the right, way to the right. As our graph moves to the right, if we move on along to this graph to the right, we're also moving up. And not only we're moving up in a really steep way. So we're moving up without bound. And that tells us as x goes to infinity, f of x goes to infinity, just as the computations told us that. Now, as we move along the graph to the left, that's as x goes to negative infinity. That means we're going to go downhill on the graph as we move left. And not only that, but we're moving down without any bound because we're moving down very, very steeply. And that tells us as x goes to negative infinity, f of x also goes to negative infinity. All right, so here's another example, a slightly more complicated function. Again, let's see what happens as x gets, well, let's do the first as x gets really big. In other words, as x goes to infinity. Well, if we put in, say, x equals 1,000, we get 1 over 1,000 squared plus 1 equals, holy cow, 9.9999999 times 10 to the negative 7. Well, I said holy cow. You can say yikes, that's fine. But what the idea is, if I put in a bigger value, it would even get more stark. As x gets really big, x squared plus 1 is going to get really, really big, right? We square it and add 1, that makes it even bigger. We take that reciprocal, it's going to get teeny tiny, very close to 0. Which tells us that in this case, as x goes to infinity, f of x doesn't go to infinity or negative infinity, it actually goes to 0. Let's see if something else interesting happens if x goes to negative infinity. In other words, when we put very negative values of x. So I'm going to, again, try x equals negative 1,000 this time. And guess what? I get the exact same thing. Because, you know what? If I square negative 1,000, it's exactly the same thing as if I square 1,000. Well, you don't have to say yikes this time. We knew that was coming. All right, so we can see now that as x gets very negative, x squared plus 1 is still going to get very big, and not just big, it's going to be big in a positive way. And so, again, 1 over x squared plus 1 is going to get close to 0. If you want to state that symbolically, that means as x goes to negative infinity, we also get f of x goes to 0. So as our end behavior can have any of many types of ways of resolving itself. It can go to infinity, it can go to negative infinity, it can go to 0. it can actually go to any number that you can imagine depending on what function that you're dealing with. And again, we can infer this from the graph. This will be interesting because I wonder what happens. Try to imagine what happens as we go x goes to infinity or negative infinity. Our function value is getting close to 0. Well, that's what happens. So as you can see, as the graph moves to the right, if we move along the graph to the right, we're going to get closer and closer and closer to the x-axis. And the x-axis is just y equals 0, right? So y equals 0 means that 0 is going to be the output that we're getting closer to. So that means as our inputs go to infinity, our outputs get closer to 0. And as we move to the left, same deal. It also is going to get closer to the x-axis, just on the other side, just on the left side of our x-axis. Again, that's at y equals 0, so as x goes to negative infinity, f of x also goes to 0. All right, so now that we've gotten our feet wet working with end behavior of functions that we're a little bit more familiar with, let's see if we can apply this to exponential functions. So our first exponential function is f of x equals 3 times 2 to the x. So let's see what happens when we put in some big values of x. If we have x equals 1,000, say, we have f of x equals 3 times 2 to the 1,000, which equals, yeah, that's a big number. Some number a little bit bigger than 3 times 10 to the 301. That means there are that 3, whatever, it has 301 zeros after it. That is a lot of zeros. That's a big number. And so what this suggests is, as x gets big, our 2 to the x actually is going to get not just big, but hugely bigger, right? And we multiply by 3, even bigger than that, which means that as x goes to infinity, our f of x is also going to go to infinity. Now let's see if something similar is going to happen when we put in some very negative values of x. Maybe that's going to go to infinity. Maybe that's going to go to negative infinity. Maybe it'll do something else. We'll have to see. So if we put in, say, x equals negative 1,000, is that going to work the same as 1,000? Well, it's going to work a little differently, because now instead of having 2 to the 1,000, we have 2 to the negative 1,000. And if you remember what happens with negative exponents, that actually means we take whatever that number is without the negative and we put that in the denominator. So 2 times negative 2 to the negative 1,000 means we're dividing by 2 to the positive 1,000. And 2 to the positive 1,000, of course, is a huge number. And I'm not going to write down what exactly that number is when we do 3 divided by 2 to the 1,000, but it is going to be a number that is very, very, very close to 0. And so, in fact, as x gets very negative, 2 to the x is going to be the reciprocal of a huge number, right? Because x is going to be a very negative number. When you flip that to make it positive, that's going to be the reciprocal of a huge, huge, huge positive number, which means that 3 times 2 to the x, making it only a little bit bigger, it's going to go to 0. So as x goes to negative infinity, f of x goes to 0. And once again, we can see that this phenomenon on the graph. So if you look at going to the right on the graph, right, as you move to the right on the graph, it's going to get higher. Not only higher, but it's going to get higher like super quickly. It's just going to shoot to the sky, right? Which means that as x goes to infinity, f of x also goes to infinity. But as you move to the left, the graph is going to get sort of a soft landing towards the x-axis. That means the y values are getting close to 0. So as x goes to negative infinity, f of x goes to 0. Now, on the in-class activities, I'm going to have you do this exact same type of analysis on 3 times 2/5 to the x, so that you can see what happens when you have a b value that is smaller than 1. So you have exponential decay. But I will give away now what the kind of the general rules are, but again, I want you to do this analysis to see if you can verify it. So if you have a times b to the x, the behavior is almost entirely, the end behavior is almost entirely determined by b. There's a little bit of influence of a, as we'll see in a bit. So if b is bigger than 1, then that's the example that we did in this video. As x goes to infinity, your f of x is either going to go to infinity or minus infinity. And if you can't see how it can go to minus infinity, you just have to imagine what happens if you have a negative value of a. If you have a negative value of a, all your outputs are going to be negative. So you're going to get infinity or negative infinity depending on whether a is positive or negative. And as x goes to negative infinity, no a can save you on that one. Your f of x is always going to go to 0. Now, if b is between 0 and 1, as x goes to infinity, in this case, our f of x is going to go to 0 no matter what. You'll see how this works on 2/5 to the x whether your a is positive or negative is going to make no difference. If they're positive numbers getting close to 0, negative numbers getting close to 0, they're all going close to 0. So that means as x goes to negative infinity, and as x goes to negative infinity, what you will see is it flips around. Either f of x is going to go to infinity, or f of x is going to go to negative infinity, and once again, that will be completely determined by the value of a. If a is positive, you're going to go to positive infinity. If a is negative, you're going to go to negative infinity. All right, so now I think you're ready to work on the activities on the PDF, and the name of that PDF is End Behavior of Exponential Functions.